we are going to look at first non-trivial algorithm called Deutsche algorithm. In some sense, it is the second non-trivial algorithm because you have already seen Deutsche algorithm. Deutsche is a generalization of Deutsche's algorithm, and you will see that it is essentially the same technique to solve a slightly bigger problem. Do you remember Deutsche's problem? It's a small one-bit problem where f is given as a black box where the bit ranges from 0, 1, and your task is to find out if f0 is not equal to f1 or if f0 is equal to f1. This problem is now generalized and it will be called Deutsche. What is the problem now? It will say that you are given a string x from 0, 1 to the n, again in query model, in the sense that you will have a black box where the input will be hidden. And you are going to query xi, you want to minimize the number of queries and solve the problem. What is the problem? You know that x satisfies a promise. That means x can't take all possible values from 0, 1 to the n. On the other hand, it satisfies a promise. What is the promise? Either all xi's are same or strings is balanced. What does it mean? It means that exactly half the xi's are 1. And this will also mean exactly half the xi's are 0. This is the constant case. That means everything is the same. This is the balanced case. It should be clear to you that this is a generalization of Deutsch's problem. If not, just view the input as a truth table. This is something we discussed in the lecture on the query complexity model, where we said that sometimes the input is viewed as a truth table of a function. And then you will see that when this n is equal to 1, then this becomes Deutsch's problem. It will exactly be the case. Constant means f0 is equal to f1. String x is balanced. Exactly half the xi's are 1. This is the case when f0 is not equal to f1. I have not mentioned it, but remember we are taking n is equal to the power k. And in that case, this will be a truth table of a function from 0, 1 to the k to 0, 1. We know that our string x is constant or balanced. This is a promise. Those are the only possible x's which will be given to you, and our question is to distinguish between the two. We have to find out where do we fall. Is the string given to us is constant or it is balanced? How should we solve it? I will give you some hints and then the algorithm will basically pop out. Remember that what is the query oracle? We saw 3 models to it. The one where we are going to use in this case is this. Remember, this was obtained by applying header mode on the standard query oracle, where the output is computed in the second part of the qubit. These two are the same. We are going to pick this oracle. This will make it easy to describe Deutsche algorithm. Now, once we are computing the oracle answer in a phase, we can rephrase our problem in terms of the phase also. We have two cases, either x is constant or x is balanced. X is constant is saying that if I look at this thing, since everything is same, this will turn out to be 2 to the k. Again, remember n is equal to 2 to the k, because all of them will have the same phase. Everything will be minus 1s or everything will be 1, and the sum will be 2k. This is the case when x is constant. If x is balanced, then these things will cancel out and this will be 0. Look at the problem in this rephrasing. We are either in case 1 or in case 2. Can we figure out which case are we in and how many queries do we need to do there? It will turn out that just one query is sufficient. Let's see how. We know that we can compute minus 1 to the xi in phase. Can we calculate this quantity in phase? And if you remember Deutsche's algorithm, you will see that this is not hard. This is basically Hadamard. I'm going to write this equation. You can convince yourself. It's not very difficult. I'm describing the action of Hadamard on state I. Remember that I am viewing I and j as k-bit binary strings. I is an element of n minus 1. It is one of the index values, but I can think of it as a k-bit binary string. That is because n is equal to 2 to the k. Here, I dot j is the bitwise dot product of these binary strings. Once I view them as binary strings, I can talk about their bitwise dot product. This action you can confirm yourself. You can convince yourself that this is what Hadamard does. Let's talk about, given this equation, action of Hadamard on 0. This is 1 by root 2k summation over j. J is equal to 0 to n minus 1. What it says is that Hadamard spreads the amplitude equally when applied to 0. Also notice Hadamard is its own inverse. And that will tell you that Hadamard will also collect amplitude. On state 0. What this means is, if I take Hadamard and apply psi, where psi is equal to, let's say, alpha I, in this case, it will be something plus 1. I don't care about these amplitudes, but this will be summation alpha j. All my amplitudes will be collected on state 0. And that is what we wanted. We wanted to distinguish between two cases. One was when our amplitudes were summing up to root the k, and the other was when the same quantity, the sum of the amplitudes was 0. Now what we want to do is, we want to get this minus 1 to the xi in phase. That will be done by applying the query oracle and then collect the amplitude by applying Hadamard. But first, spread the amplitude first on everything so that when we query everything. This basically means that our algorithm will look like Hadamard, phase, Hadamard. I should say this is the query oracle. Intuitively, we spread the amplitude to all states so that when I query all states together. Then we query all states in superposition. Now the amplitude will be in phase, sorry, now the function value will be in the as a phase in the amplitude. Then we collect all phases by Hadamard. Then the summation will be at the state 0. Fourth step, measure 0. If, or let's say 0 perp, in this basis we will measure. If we get 0, that means this was the case, the function was constant, that's why there was an amplitude. If this was the case, then the amplitude of state 0 will be 0. Then we will get not 0. That means balanced. This is the complete algorithm. If I want to make a circuit diagram for this, not going to be very difficult. I'm going to have k qubits. These are my starting qubits. All of them will be in state 0. This will be the qubit for my oracle. I will first spread my amplitude to everything. This will be done by a Hadamard. Now all i's will be queried. This is oracle with 1 so that my xi goes into the phase. Then again by applying Hadamard, I collect the phase. Final step is to measure amplitude on 0. That is to say, if my projector on 0, 0 is P0, I will measure on P0 and P0 perp, or P0 and I minus P0. If I measure this, that means the function is constant. If I measure this, then the function is balanced. You can easily notice that if I wanted to find this property by any deterministic algorithm, I need to query at least n by 2 bits, that is at least these many queries. But a quantum algorithm does it in O1 queries. You might ask, what happens if we query in a randomized manner? That means we use some probabilities to query something, because quantum is inherently probabilistic. Probably that's the right model. That's a valid question, and we will first learn what does it mean to do randomized computation. And then we will see examples which can distinguish quantum computation and randomized computation. But that will be the talk of next week.